Okay, everybody, welcome back to the last topic of the current unit. This topic is all about isosceles triangles and equilateral triangles. We have four new theorems to prove today and several examples to go along with that. And then you'll have the assignments after that. Okay, so a little bit of vocabulary first. If you look at the drawing here, you see a picture of an isosceles triangle. Remember we said an isosceles triangle was a triangle that has two congruent sides. And so if you look at that drawing, you see them, and they're called legs there. They're marked off, and they're called legs. So the congruent sides of an isosceles triangle are called legs. The other side is called the base. So you can see all that on the diagram. Where the two legs come together, they're going to form the vertex. So you see that on top. And then the angle there, which is angle 3 at the vertex, is called the vertex angle. The other two angles are 1 and 2. They're called base angles. So those base angles are, you see them down there. The base is included between those two base angles. So there's some of the vocabulary dealing with an isosceles triangle. Let's dive right into our first theorem. This is called the isosceles triangle theorem, and it says if two sides of a triangle are congruent, then the angles opposite those sides are congruent. So you're given in that diagram that side AB is congruent to side AC. That's marked off there. And you're trying to prove that angle B is congruent to angle C. Okay, so we have the three elements for proof there. We have a diagram, and then we have what's given, and then also what we're trying to prove there. Okay, so let's to prove this, let's choose a point here. Let's just call it X. It's the midpoint of segment BC. So I'm going to call that X. That's the midpoint of segment BC. And we're going to connect that then with the vertex. So let's just connect that up there. So because we designated that point X to be the midpoint, then we now know that BX and CX are congruent by definition of a midpoint. Okay, we also see that AX is congruent to itself. And so now we see that the two triangles are congruent by SSS. Two triangles are congruent by SSS. And keep in mind what we're trying to prove. We're trying to prove angle B is congruent to angle C. And if you look at angle B and angle C down there, those are going to be the two angles that fall on top of each other if you line these two triangles. So those are corresponding parts. And we know that corresponding parts of congruent triangles are congruent. So that tells you that angle B is congruent to angle C. So again, the theorem, it's called the isosceles triangle theorem, says if two sides of a triangle are congruent, then the angles opposite those sides are congruent. Another way to say that, if you are in a hurry, is base angles of an isosceles triangle are congruent. Okay, let's take a look at then actually the converse of that, the converse of the isosceles triangle theorem. That's when you switch the hypothesis and conclusion. So the converse says if two angles of a triangle are congruent, then the sides opposite those angles are congruent. So we literally just switched angles and sides. So in this diagram that you see there, triangle DEF, we're given that angle E is congruent to angle F. And we're trying to prove that side DE is congruent to side DF. Okay, so what we're going to do to prove this is we're going to draw an angle bisector here. So we're going to bisect that angle D. So that's an angle bisector. Now here's what, and I'll call that point X down there as a point of reference. Notice that just because we bisected that angle, I mean, we can actually mark these off as being congruent because we said we bisected that angle. But we now cannot say that X is a midpoint of segment EF. We don't know that. All we know is that we bisected the angle up there. So now we've got two angles on one triangle congruent to two angles of the other triangle. Notice we also have side DX is congruent to itself by reflexive property. So now we have enough to conclude that those two triangles are congruent, and they are congruent by angle side. All right, two angles on the non-included side of one triangle are congruent to two angles on the non-included side of another triangle. So now if you took one triangle and put it on top of the other one, we would see that segment DE and segment DF coincide, that they correspond. They're going to fall on top of each other. And so we can say the segment DE is congruent to segment DF by corresponding parts of congruent triangles are congruent. Okay, so now we know both the isosceles triangle theorem and the converse of the isosceles triangle theorem are true. We proved them. Let's do a couple examples before we move on to the next two theorems. So if you look at this example, we have triangle ABC here, and we know that it's an isosceles triangle where you marked off two sides are congruent. And now we have a theorem for that, which says that if two sides of a triangle are congruent, then the angles opposite those sides are congruent. So we know that B and C are going to be congruent. So if we just take the 180 that we know minus the 38, so 180 minus 38, we're going to get 142 degrees. So now that we know that angle B and C are both equal and they have to share that 140 degrees, it's going to be 142 divided by 2, so each one's going to be 71 degrees. So we found angle C and angle B to be 71 degrees. Okay, so we use the isosceles triangle theorem to solve that one. Let's do another example before we have our other two proofs. So look at that one also. So again, you got two sides of a triangle that are congruent, and then the angles opposite those sides must be congruent. So R and S are the angles that must be congruent. So we're going to set those equal to each other. So we have x plus 30 is equal to the 2x. So it looks like 30 is equal to x. Okay, so don't forget we got to go ahead and find the measure of angle S. So the measure of angle S is going to be 2 times that 30, so 60 degrees. All right, so we use the isosceles triangle theorem on that one. Okay, we got a couple more theorems that we're going to prove here, and then we'll have a couple examples after that. Okay, now we're talking about an equilateral triangle. So if a triangle is equilateral, then it is also equiangular. So remember, equilateral triangles have all the sides equal. So you see triangle ABC there, it's given to be equilateral. So I've got all the sides marked off there, and we're trying to prove that it is equiangular. Okay, let's think about this for a minute. We have the isosceles triangle theorem that says if two sides of a triangle are congruent, then the angles opposite those sides are congruent. So we know that since side AB and side AC are congruent, then now we know that angles B and C are congruent by the isosceles triangle theorem. Now let's choose a different pair of congruent sides. So we now know that side AC and side BC are congruent because that's an equilateral triangle. Then the angles opposite those sides must be congruent. That means B and A must be congruent. So think about that. We got angle B congruent to angle C. That was from taking two sides of that triangle to be congruent. We also have now angle A congruent to angle B by choosing a different pair of congruent sides. So by the transitive property, angle A is congruent to angle B is congruent to angle C. They're all equal. They're all congruent. The angles are congruent. So that means that triangle ABC is equiangular. And we also know that those angles would be 60 each. So the theorem says if a triangle is equilateral, then it is also equiangular. Okay, let's take the exact converse of that theorem for our last theorem. And this one says if a triangle is equiangular, then it is equilateral. So again, we're given triangle DEF. This time I'm marking all the angles congruent because that's part of the given. And we're trying to prove that the sides are congruent. Okay, so you might remember the converse of the isosceles triangle theorem says if two angles of a triangle are congruent, then the sides opposite those angles are congruent. So if you say that angle E and F are congruent, which is part of the given, now we know that side DE and side DF are congruent because those are the sides opposite congruent angles. Okay, now let's consider a different pair of congruent angles. So let's say angle D and angle E are congruent, which they are. It's part of the given. That means that side DF and side EF are congruent. So we see from that all three sides are congruent. And so we had side DE congruent to side DF to begin with. And then we saw that side DF was congruent to side EF by just choosing a different pair of angles that were congruent. So again, by the transitive property, you have segment DE congruent to segment DF, which is in turn congruent to segment EF. And so all three of those segments are congruent by the transitive property. And so that makes that triangle equilateral. So if a triangle is equiangular, then it is also equilateral. Okay, let's do a couple more examples, and that'll wrap up the notes here. So in this example, you see that you have an equilateral triangle, and we know that if a triangle is equilateral, then it's also equiangular. And so we're trying to find that angle there, actually angle C, which helps us find x. So we know that if a triangle is equilateral, it's equiangular. So the triangle is equiangular. That means each of those angles are 180 divided by 3 is 60. So our simple equation is to take 3x plus 15, set it equal to 60. So 3x is equal to 45, makes x equal to 15. So that's all we have to do. We had to find x, and it was 15. We did not have to go back and plug in anything to get an angle. And it looks like our last example involves an equiangular triangle. So there's an equiangular triangle. You can tell by the markings. We have a theorem that says if a triangle is equiangular, then it's also equilateral. So we know just from that theorem that those three sides of that triangle are going to be congruent. And so we'll just simply set 2t plus 1. So 2t plus 1 equal to 4t minus 8. We'll solve that for t, because that's what we're trying to do. So we got 1 equals 2t minus 8. Subtracted 2t from both sides. Let's add 8 to both sides. So that'll give you 9 equals 2t. And t is 4.5. Okay, so let me do a quick summary of what you need to know in this last topic of this unit. And that is that we're talking about isosceles triangles and equilateral triangles. And we had the isosceles triangle theorem, which says if two sides of a triangle are congruent, then the angles opposite those sides are congruent. Then we had the converse of that, which said if two angles of a triangle are congruent, then the sides opposite those angles are congruent. Then we had two theorems dealing with equilateral triangles and equiangular triangles. The first theorem there said if a triangle is equilateral, then it is also equiangular. And then the exact converse of that is if a triangle is equiangular, then it is also equilateral. So there you go. That's the last unit. We have 2 assignments that go with this material, so they're posted. So go ahead and let's get started on that, and we'll talk to you later.